We have this rule, this good looking rule right here. And actually I can close down the calculator for a little while. So probability of B given A is equal to the probability of A and B divided by the probability of A. Right? So this vertical line here means given. I'll actually just draw an arrow to it. Given that, or such that, say it different ways, but you could say knowing that, right? So when I say probability of B vertical line A, I'm really saying to find the probability of event B given that event A has occurred. All right. Gotta apologize for the penmanship. It's unfortunately the best I can do. My it's a nerve thing. It's been acting up. So you'll see there's at least an attempt to be kind of legible early on, but then it kind of goes off the rails at the end of each line. I don't know why. Physical therapy or something. So it's saying find the probability of event B given, or you could say event B occurring given that event A has occurred. Right? And it's not always the easiest thing in the world to determine, but if we follow this rule, we can get there pretty quickly. The thing is, when the information is not presented in a table, that's when it gets a little trickier. Right? We're only going to focus on the cases that involve tables, or cases where we have to make a table and then use that table to determine the probabilities. Right? So, and there's a nice little shortcut to the formula. I'll show you that in a minute. But we'll do it the quote-unquote long way first. Right? So looking at example 1, it's the probability of yes given that the ages are from 16 to 25. All right, so the table is a result of 100 randomly selected people entering an amusement park who were asked whether they were planning on riding the Monster Loop roller coaster. Monster Loop, insert your most terrifying roller coaster in place of that's really the object of the question. All right, so like Sky Rush at Hershey Park or something. I don't know. I won't get on that one. I'll get on some of the other crazy ones, but I won't get on that. It's the height that gets me. So, but maybe younger people are less concerned with that thing. That idea that something may go wrong on a roller coaster, and and it'd be terrible. Older people may be a little bit more aware of that possibility. All right, so that's what these questions are getting at. So probability, the B is going to be yes, and 16 to 25 will be the A. All right, so when I say find the probability of B given A, so applying this formula, it's again going to be the probability of A. I really should have used the proper notation here. It should be the intersect. Oops, see, handwriting gone wrong. All right, so A and B divided by the probability of A. All right, so if I follow this model using their definition of B and A, I would come up with the probability of yes, I guess you don't need the quotes, given ages 16 to 25 would be equal to the probability of yes and the ages 16 to 25 divided by the probability of getting a person who is in the age group of 16 to 25. So age is 16 to 25. All right, so it's kind of notation heavy at this point. But again, I mentioned earlier that we're going to do a much more streamlined approach in a couple minutes. We're not going to do the long way every time. All right, so just this gives you a sense of what's going on. So in the case of yes and 16 to 25, it's kind of like a Venn diagram in the sense that you're looking for the intersection. Right? This Venn diagram would be monstrous. We would have all the different ages and all the yeses and nos. So you'd have, 6 circles, and how they overlap, that would be problematic, right? At least physically to draw it. But in the form of a table, we could just say, all right, I'm looking for yeses and ages 16 to 25. So it's kind of like how we looked at the deck of cards, where you'd say, I want a card that's red and 7. So you look at all the reds and all the 7s. The ones that are red and 7 should be the overlap. All right. So that happens right here. So the probability of being a yes and in the age group of 16 to 25 would be 23 over whatever the total number of individuals is. Now, they told us up top here that there's 100 randomly selected people. I suppose we could verify that by getting some totals here, across the line here, create a total column. So 32, 40, 54, 19, 31, 36. Oh, you know what? I made a typo on this a while ago, and I never got around to fixing it. This doesn't add up to 100, it adds up to 90. So this is actually a typo here. It should be 90 randomly selected people. I guess I could just change numbers in a table, but I think it's a little easier to make that fix. Then to get the totals, I'm just going to move this real quick. I'll just put it here. To get the totals for each individual column, just add down the line 17, 34, 20, and 19. All right, so 17, 34 is 51, 71 plus 19 is 90. All right, so we have a total of 90 individuals that are in this study. So the ones that said yes and are in the age group of 16 to 25 would be 23 out of those 90. Right. Now, if I'm just looking at the number of individuals who are in the 16 to 25 group, that would be this value here. 34 out of the 90 available individuals. Now, if you have a complex fraction, a fraction over another fraction, if the denominators are the same, you can just cancel them out. All right. It's basically a shortcut to keep, change, flip. So this would simplify down to 23 over 34, right? And if you're not sure, just use a calculator. And it's not designed to be, the computation in this course is not designed to be overwhelming. It's really more about the thought process than anything else. All right. So I prefer the NumWorks calculator. There's an app for your phone for that. I'm not going to make you buy one. I mean, if you have one, you can use whatever calculator you want. It's fine. Question. Well, I guess it's the point of saying we didn't know that we would cancel it later. I did because I've done this problem 30 years, but that's the big reveal. Yeah. So now we know that we didn't have to bother with the 90. So that's going to lead us to our shortcut.
Is there a scenario where it would be 23 or 90 or
Not for these kind of problems. Yeah. Good question. All right. So in the case of, and I'll just look at number 2, for example, to show you the shortcut. If we go by the strict definition of B given A, find the probability of event B given that event A has occurred. All right. So this is my given. Let me use a different color here. All right. So without using the formula, we can now say, all right, if it's a given fact that the age group is 26 to 35, let's just focus on those individuals. All right. So let me get rid of this row of highlight here just for a couple minutes. So I'm just focusing on the individuals who are in the 18 to 35 group. So all of these folks. And from there, I want to identify anyone who said no. So it's kind of like you're taking the table and trimming it down so that this is like my new table. All right, we're ignoring everything else. So these would be my yeses, these would be my nos, and this would be the total number of people that fall in this group. So what I could just say here is, if I'm looking for a no, out of the 20 available individuals, 12 of them said no. All right. So that's the shortcut, so that you don't have to go through and basically do all this. All right. We don't need all that, because we could just jump right to it, which is really nifty when it comes to analyzing data from a survey. Just going to put this back now. All right. So I would look at, for the next one, I'd have my given here. I'll go blue for those keeping score at home. My given is the no's. From that set of no individuals, I just want anybody who falls in the age group of 26 to 35. All right. So there's 36 individuals in the no group. All right. Just going across the no line. See that we added it up and it gave us total of 36. The ones that fall in the 26 to 35 category, these folks are the ones that I want. All right. So 12 out of 36. And that would be the probability. So, I mean, if you reduce that, you get 1/3. So it's basically saying, all right, 1/3 of the people who said no came from the 26 to 35 age range. And see how the table gets a little crazy after a while. So an eraser is probably not a bad idea, but most of the time what I do is I just use my fingers and say, all right, this is where I'm focused. This is my given. That's my total. What number am I looking in relation to that? So I would say, I'll use my virtual finger here. So these are my no's, this group here. Then I would look in this entire little subset here. All right. Anyone who is in the 16 to 35 range, which would be these 12 folks here. All right, so the 12 out of the 36. All right, so all of that would be kind of happening without me doing any writing. All right, that's kind of the idea. All right, I'm going to slip in one more example related to that. I'm going to clean up this. I'm going to bring it all back in a little while, but actually I need the totals. So I don't want to clean it up too much. Just gonna kind of swing this. Say it again? Yeah, okay, so I'll do that. So we're looking at only the individuals who said no. So that would be this group here. All right, so ignoring the rest of the table. The rest of the table does not exist. This is all we care about. Then from this set, I'm just gonna look for anybody who fell in the 26 to 35 interval. All right. So in that blue line, there's only one cell that contains the 26 to 35 individuals. And that's those 12 people. So it would be 12 out of the 36. I'm going to do another example. Let's see. Let's say, actually, I'll do a little comparison. This would be a pretty good example. And you know what? I'm going to use this to replace number 4. Something popped up on the big screen over here. It was like weird. So, new number 4. What is more likely? probability of saying yes, given that you're old, or, and we know being over 36 is not old, but in comparison to the 8-year-olds, yeah. You ask an 8-year-old, like if you're like, let's say 25, and you ask an 8-year-old, how old do you think I am? They come back with, I'm not sure, you're just old. And it's like, oh, I think you're like 47. It's like, no, I'm not. Or at least I wasn't then. So we'll say yes, given that you're in the young group, 8 to 15. All right, so that's kind of a new number 4, a better number 4, I would say. Just a better question, because this is more like probability theory. I mean, there's a place for it. It's just we want to get to where this is useful. So, more theory doesn't really serve that purpose. So again, diagram gets pretty messy pretty quickly. So I'm just going to kind of take all the bits and pieces out, all the highlight. We'll look at being in the 36 or older group. That's our given. So that would be these individuals here. So that makes the 14 our yes, because you see how it compares or cross references with the yes row, the no, and the total. All right. Basic definition of probability is part over whole. How many ways can you get what you want? How many ways can you get something? All right. So the yeses account for 14 of the 19 people. All right. And then we do the same thing. Just this time we're looking at the 8 to 15 group. So it amounts to the yes, the no, the total. All right. So we're looking at 9 individuals in this group who said yes out of the 17 available. All right. So the ultimate question here is what's more likely? It's sometimes hard to tell when you look at fractions with weird denominators. And so that's where you get your calculator involved. Let me see if I can easily bring it in. Not easily, but I can bring it in. All right, so we're looking at these two numbers, 14 out of 19. Let me just clear this out, different class. So that's about 0.767. Sorry, 737. And again, I mentioned before that we don't want to go to decimal form very often. Most of the time it's just fine to put the fraction answer. Just I need to be able to compare these two numbers, and this is the best way I can think to do it. All right, so the 9 out of 17 is about 0.529. All right, so what this is saying is the 36 plus group is more likely to say yes. All right, so answer. We don't need probability anymore. Well, I guess I could put it in there because it did phrase it that way. All right. What this is saying is more of the 36 or older group were ones who said yes than individuals who are in the 8 to 15 group. Right? Now, probability is a tool it's an investigative tool. We use this tool to help us draw meaningful conclusions from situations. The probability question, I mean, in the past it was like just an exercise, like, oh, I want to know how many ways I can get a winning score, a winning combination if I play a lottery or something like that. It's like it's a number. But when you can compare it to something else, it takes on more meaning. Right? There's more value to it. Right? So that's what we're working towards, using these probabilities to help us, analyze situations. And you'll see as we go forward, we'll work with more real life instances where, what's more likely, me winning the lottery or striking it rich in the stock market. It's a very basic example, but like the lotteries that we'll work with, like Mega Millions is one thing, or Powerball and stuff like that. Like the probabilities are so infinitesimal that you wouldn't look at that as a likely occurrence anywhere. But if we take like the daily number and compare that to buying $20 worth of stock in Ford Motor Company and then pulling that money out after 2 days, like which is more likely to give you the jackpot in those instances? Yeah. So that's just something that we'll talk about, but yeah. Let me just get rid of this. Like I said, number 4 got changed. Number 5 is a good kind of Venn diagram-ish question, but like I said before, when we deal with conditional probabilities, we tend to make a table out of it. So you could draw a Venn diagram, and I'm sure it'll look gorgeous. I can do it real quick. It's not going to be a problem. I was just making sure the numbers worked out this time because I'm having a flashback to this example where the numbers didn't add up. Anyway, sample of 40 vehicles. You have 8 are red, 6 are trucks, 2 are both. Suppose that a randomly selected vehicle is red. Determine the probability that it's a truck. All right. So, I mean, we could actually figure it out just by the context, but I'm going to show you the table approach. So we have trucks, well, really trucks and non-trucks. So we have red and not red. So say red, not red. Truck, not a truck. This one actually isn't my fault. The connection between the Apple Pencil and the screen just kind of glitched for a sec. So truck and not a truck. All right. So we have 18 vehicles that are red. So if I were to go across the red line, I'd have 18. All right. I have 6 that are trucks. So if I go down the truck line, I would get a 6 here. That's my set of totals. All right. Then we have 2 that are both. All right. So that's red and a truck at the same time. And we know that there's 40 vehicles in total. All right. So that would be my grand total. The total of the totals is also known as a grand total. All right. So I can use that information to figure out everything else in the table. So this problem's more about you learning how to build a table than it is to actually answer the question. If there are 6 trucks, 2 of them are red, then 4 of them must not be red. All right. If 2 of the vehicles, I'm sorry, I was going to say that, right? If 2 of the vehicles are red and there are 18 red vehicles, this is just, the formatting just got so crazy here. All right. So I have 2 red vehicles, those are the trucks. Then I must have 16 red vehicles that are not trucks. All right. If there are 18 red vehicles and there's 40 vehicles overall, that must mean that the other 22 vehicles must not be red. If 4 of the non-red vehicles are trucks and there's 22 overall, it must mean that 18 of those other colors, not red, must be not trucks. And since we know that there are 16 red vehicles that aren't trucks, they could be sedans, they could be SUVs. I mean, it depends on how you define a truck, I guess. And we know that there are 18 vehicles that are not trucks and also not red. That means that we're looking at 34 vehicles that are not trucks in general. All right. So to answer the question, now that we have a table, I'm actually going to throw in another question to sort of make it worth our time to actually make the table. But let's do the first one. So it's a probability of a truck. They use lowercase, so I'll use lowercase. Given red. And then we'll also find the probability of it not being a truck. I'm using a little not symbol there from logic, given that it's not red. All right. I'm just going to shimmy this over to the left there a little bit. All right, so a red vehicle. So in my set of reds, I'm looking for any trucks. All right, 2 of the vehicles in the red category are trucks, so 2 out of 18. Then for the set of not red vehicles, from that set, we're looking for vehicles that are not trucks. So 18 of those 22 vehicles are not trucks. Now for this, I don't think we need a calculator to compare. And also, I didn't design the question so that we had to compare. But I would look at this and say, well, it's more likely that it is not a truck if it's not red. Right? So meaning it's some other vehicle if it's not red. So I kind of look at it like, all right, so you picture, and you can collect data related to this fairly easily. You just stand at an intersection, not tonight when it's pouring, but on some nice clear day, just stay there for like 10 minutes or so, 5-10 minutes, and just take note of the type of car and the color of car that drives by, right? It's a form of sampling, and I'll talk to you about that as we go forward, right? But what this is saying is that it's less likely that it's a truck if it's red, right, than it is if it not being a truck if it's not red. Right? So if I see a blue car that just drove by, right, then I'm looking at that and saying, well, that's not red. It's most likely not a truck, right? Based off of this data. Now, if I were actually collecting the data, I wouldn't limit it to just red and not red. Right? But I had a student who did it, this is like 15 years ago now. Like when I ask students to collect data, it really stinks because a lot of the time people just make up the data. Like if I say, is it more likely that you'll get pulled over if you have a red car than some other car? People go online and try to find some data. This student actually went to the Peekskill Police Department, and they told them that she was a student, and that the purpose of the study, and they gave her a month's worth of ticket data. Vehicles that were pulled over. She was focusing just on speeding because it's kind of tough, like with different types of violations that you could have, right? And you never really know, like, you get pulled over for obstructed view. Now, you probably didn't get pulled over for obstructed view. You got pulled over for speeding. And they just put it down as obstructed view because they're being nice on Interstate 87 a week and a half ago around Lake George. Nice guy. Yeah. It's like, like when they know you're from out of town, the cop's probably more likely to. I mean, if you do the right thing, like you get pulled over, yes sir, no sir, all that stuff, they're more likely than not going to at least try to do something for you, right? So fortunately, this trooper was pretty nice. So yeah, this student collected data and determined that there was no significant relationship between the color of the car and getting pulled over for speeding. All right. So then, like we always hear that, red cars are more likely to get pulled over for cops. But she somewhat conclusively determined that it's not all types of violations, right? Because speeding didn't show a significant relationship, right? So you think about the other types of violations that one could get pulled over for, right? And then combinations of things. You had a bright red car and also really dark tinted windows. Are you more likely to get pulled over for that? Common sense tells you yeah, but collect the data and find out. That's why we do this stuff. All right. So that's something that's coming down the line. I'll talk to you about different studies that you can do, data collection and analysis. Because I feel like probability, it really doesn't. I mean, we could take a test on it, and some people like to do tests more than like small projects and things like that. But I feel like probability statistics are things that really need to be applied in order for you to understand it. Like I can ask you a question on a test in a sample of 40 vehicles, 18 are red, 6 are blah, 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 and I'm sure it would be meaningful to someone. It isn't until you yourself collect the data that you really start to see the power of this kind of stuff. Right? And to that end, we need to learn about something called counting, which makes it seem like, okay, this is a topic that we're covering about 20 years too late. Like, this is a kindergarten topic. You're counting. They call it counting. I call it a shortcut to determine the total. Right? So if you have a need for whatever reason to determine the number of people who are in this building right now, I mean, you could go to every room and count, physically go 1, 2, 3, 4, 5, and so on. Or you could go into the room, ask the professor, do you know roughly how many people are in this class? They'll say 20, 25, whatever. You make a note. You just saved yourself some time. All right. Maybe depending on whether the teacher wants to ask you why you need to know and stuff like that. All right. So this is along those lines. It's a shortcut to determining the total number in a set. I start off very basically. Right. So we start off with a factorial. Right. So a factorial is a useful way of determining the number of arrangements in a set. So I'll give you the example. A group of 4 people must be arranged in a line. All right. Now, again, it's simplistic, but take that and apply it to something meaningful. And by the way, it's simplistic because we have to start somewhere. But if you're looking for the number of ways to win the daily number, or win 4, I think it's called win 4, it might be pick 4. That depends on the state. That's this question, right? Just tweaked a little bit. So there is a meaningful application, but we got to start small. All right. So 4 people have to be arranged in a line. We'll call them A, B, C, and D because I'm really creative. All right. So position 1 could be any of the 4 people, A, B, C, D. Any one of them could occupy the first position. Position 2, position 2 could be anyone who's not in position 1, right? Because you can't occupy 2 different places at the same time, right? Heisenberg uncertainty principle? Maybe. Anyway, if person A is occupying the first position, then it could only be person B, C, or D that occupies the second position. If person B is in the first position, can't be B in the second position, so A, C, or D. If person C is in the first position, then it could be A, B, or D. If person D is in the first position, then it could be A, B, or C. All right. Now you can see how it's kind of getting a little more busier in terms of the look of the picture, but we are getting fewer and fewer possibilities as we go position by position. All right, so position 3, well, we could follow the trend for position 1 and 2. Position 1 had four possible outcomes. Position 2 had 3. And we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 outcomes. That must have come from taking the 4 and multiplying it by the 3. All right, so following the logic of it, if there's 4 people that could occupy the first position and only 3 for the second because 1 has been accounted for, in the third position, we would lose one of the people that are in the second position. So, for example, if it's A and B occupying the first 2 positions, then it would be C or D occupying the third position. All right, so we get fewer and fewer. I'm just gonna make my my branches here down the line. Do it exponentially. Kind of moved further and further away from where I wanted it to. So let me just clean it up a little bit. All right, so if A and B are in the first 2 positions, then it's either C or D for the third position. If it's A and C in the first position, then it's either B or D in the second position. If it's A and D in the first 2 positions, then it could be B and C in the third position, and so on down the line. All right, you can see how it gets a little compressed. So BA, well, it could be C or D. BC, it could be A or D. BD, it could be A or C. CA, it could be B or D. If it's CB, so we're up to this one, it could be A or D. CD, it could be A or B. DA, it could be B or C. DB, it could be A or C, and DC, it could be A or B. Now there are some repeats along the way here. So if you look at, ABC, for example, that first branchway here, you could look at that and say that that's the same as saying BAC or CBA. All right, we have to keep that in mind. When we're talking about arrangements, any possible way that the individuals can be grouped counts as part of the arrangement. All right. It's the context of the situation that's going to tell us whether we need to eliminate repeats. So then the last possible position would have to be whoever's left over. So that's position 4. All right. So D, get my lines in again. Just try to do it where I don't need to make any corrections afterwards. Probably just going to be easier for me to just draw them as I go. All right, so ABC must be D, ABD must be C. So the last value is actually picked for you by making the first 3 selections. All right, so that's something else to keep in mind. A, C, B, D, A, C, D, B, A, D, B, C, A, D, C, B, B, A, C, D, B, A, D, C, B, C, A, D, B, C, D, A, B, D, A must be C, B, D, C it must be A, C, A, B must be D, C, A, D must be B, C, B, A must be B, D, sorry. C, B, D must be A, C, D, A must be B, C, D, B must be A, D, A, B must be C, D, A, C must be B. And I know it's very tedious, but whenever I don't do this, students kind of lose the meaning of what combination counting and combinatorics are all about. So as tedious as it is, and we're almost done, we do it the one time just so you could see how many possibilities there are and how difficult it is, even for a small set, to come up with every possible arrangement of outcomes. All right. So I didn't clock it, but that took a good few minutes to do. All right. Now, again, we had 4 possible outcomes for the first position. Depending on who was selected, you had 3 additional possible outcomes. That's where the 3 came from. All right. Depending on who was selected for the first 2 positions, we only had 2 folks left over for the third position, and only 1 individual left over for the last position. All right. This gets at the idea of multiplication, and we end up with the result of 24, which is great. 24 possible outcomes. Would have loved to have been able to do that a little quicker. All right. Which brings us to this notion of a factorial. I know it's at the bottom of the screen there. I know there's some blockage there. But there is a function built into pretty much every calculator for a factorial. I'll tell you, in the NumWorks, it's in the little toolbox here. All right, in the toolbox. And I'll make a note of this in a minute. But you go down to probability, select combinatorics. It's like a rabbit hole situation. And then you'll see an N with an exclamation point. All right. So if you're using NumWorks, it's toolbox, probability, combinatorics, and then the one that says n factorial. All right. And again, this NumWorks that I have up on my screen, that's the same one that you would get if you download the app for your phone. All right, so, and it's free. And it's constantly getting updated. So, a lot of different reasons why you should get that. All right, so I'm going to select OK for the n factorial. It just brings up it doesn't bring up an n, it brings up just the factorial symbol. It's an exclamation point, but we call it factorial in math. Pop in the 4 and then hit OK, and it spits out the 24. All right, because 4 factorial is by definition 4 times 3 times 2 times 1. All right, so it's not like we created a factorial because of this kind of situation. The factorial concept, it already exists. It has to do mostly with this kind of scenario. All right, so it's recognizing the fit of the tool to the whatever it is whatever problem you're trying to solve. right? But this will spit out the 24 without doing all the intermediate stuff, right? And there are some shortcuts, but when it comes to factorials, I mean, you could already see if I had a group of 14 people, this would be a nightmare. Number of different arrangements for 14 people. That position 1 would have 14 people. Position 2 would have 13, then 12, then 11, all the way down to 1. That could be a little much. But we can now evaluate those kinds of situations by using this factorial tool and get at what the total number of possible arrangements would be based off of that, the initial quantity. There's a general rule there. If you like general rules, by all means, but we're going to go with the calculator approach here. Now, a line consisting of 2 people must be arranged from a group of 4. So it's like, we're going to do the whole thing all over again. But it has the same parameters of what we just started with, or as what we just started with. So if I take my tree diagram, I know you can't copy paste, but it's not going to be this elaborate. You take your tree diagram and just get rid of positions 3 and 4. Now we have a line. Now, it's not much of a line, but we have a group of individuals, 2 to be specific, from the available group of 4, right? So here we just did the 4 times the 3 to get the 12, right? So there's 4 times 3 gives you 12, and this would be much simpler, computationally, or even in the form of a tree diagram. I mean, if I tell you that you need to come up with a tree diagram, and you're starting with 4 individuals, and then after that you're going to remove 1, indicate all the different ways in which you could have a person occupying the second position, it's not that bad, right? It only got crazier as we went further down the line. This is we call it a truncated factorial, or you could call it, I put it in text there, a limitation of a factorial, right? So what we're really looking at here is that you have 2 available positions, but 4 people to play around with. Right, you kind of look at it like, you're playing musical chairs. There's 4 chairs. And people walking around the circle, and the music's playing, and then they take 2 chairs away. Then the music stops. 2 people are going to be out of luck, right? So that's what's happening here, is that these are the number of different ways that any of the 4 people available could be part of the new group, which would be the people who actually got in the chair. All right. The other 2 actually make up their own arrangements, but we don't really care about what order they happen in. All right. So that's what makes counting principles kind of tricky, is that in one instance we might care about the order, like in the case of a line. Who gets to be the leader of the line? If you're a kindergartner, that's really important to you. All right. Who gets to be the leader of a line? You're 30. I don't care. I'll get on the line. Where are we going? We're walking down the hall? All right, cool. Let's do it. First, last, second, doesn't make a difference. All right. In the case of musical chairs, I would imagine you don't care what particular chair you got, as long as you got a chair. All right. So, yeah, two seats were removed. You had 4 initially, 4 people. You took 2 away. You sat down in the seat that was closest to you. You didn't care which one it was. You just cared that there was a seat there for you. Just like the people who got eliminated don't care whether they were the first one or the second one to get eliminated. I lost. I'm out. That's all that matters. All right. Whenever we limit a permutation, we get something called a combination. But let me just show you very quickly how to do this in the calculator. So if I have a restriction on a factorial, I would use it's in the same menu, so the toolbox. You go to Permute, right? So that's Permute, and it says N comma K. All right, so it's the same menu. So when you select that, it leaves a couple of blanks there for you to put the numbers in. So we're going to permute 4 by 2. All right, this is the number of individuals available number of positions available. All right, number of individuals available, number of positions available. So you have 4 people playing the game, but there's only 2 ways to win. This would give us the number of ways in which you could be one of the winners. All right. Context usually drives this. So you just got to, kind of read the situation. I look at it like if you have a bunch of runners, they're running in a race, and they're all roughly equal in ability. They have all roughly the same speed. Like what do you say, 40 meter dash, I guess. It's something simple, 40 yards, if you're like at the NFL Combine or something. Roughly the same ability. Like, what are my chances of being in the top 3? That's what this will help us determine. I also kind of look at it like in the NFL Combine, when they do the 40 yard, you look at it and say somebody ran a 4.62 and somebody else ran a 4.44. You're like, it's such an infinitesimal difference. I mean, what's the big deal? One of them is like an all-world runner, and the other is like just okay. So they're all in the same class. It's just a question of sometimes who had the better breakfast that day. I don't know. It could be something as simple as that. But when all things are roughly equal, you could use something like this to determine what your chances are of being in the leading position. Another example, if and let's say it's a race and there's 10 people, and the first 3 people get a prize, all right. But the first prize, your first place, you get a valuable prize. Let's say you get a check for $10,000. The second person gets a brand new flat screen TV. All right, there's significant drop off there. All right, that is not valued at $10,000. And the third person gets a $50 Starbucks gift card. It's like, it really kind of matters whether you're first, second, or third. Right? So not only do you want to be in the top 3, but you want to be in the top of the top 3. Right? So permutations help us figure that out. Right? But the tricky thing is, it depends on whether or not the individuals are roughly equally ranked, ability-wise. The NBA lottery, the draft lottery to determine who gets LeBron James versus who gets anyone the Knicks took. It's like they have a system that's fairly similar to that. Like if you depending on where you are in the final standings of the previous year, let's say you're the worst record in the NBA, then you'll get the most lottery balls in the lottery machine. I probably should know what that's called. I don't. Like when you do the daily numbers, the first ball up is 1, the second is 7, and the last is 3. So the NBA works very similarly to that. So like if the Knicks had the absolute worst record, they would have the most number of lottery balls that have a Knicks logo on it. Right? And if you're, let's say, the 10th worst team, you'll get some lottery balls in there, but it won't be anywhere near as the number that the Knicks would have. Although the Knicks are not they're not terrible this year, so they probably would stay out of the lottery, I think. But yeah, so it matters how many lottery balls you have, and it happens because it is left to chance, assuming there's no conspiracy theories. It happens that a team with like the eighth worst record gets the first overall pick, just because their lottery ball came up. Right, so it's a nice little application of this, and I'll show you how lotteries work in more detail as we go. Right, but sometimes you don't care about the order. You have 4 students in a class. Determine the number of 2-person groups that can be generated from the available students. All right, so I'm going to go back, and I'm going to take this tree diagram here, which has 12 individuals, and I'm just going to tell myself, I don't care what order they're in. I just want 2 people from this group. All right, so you kind of look at it like you have something really heavy in your hands. You know, like you're trying to carry a couch up a flight of stairs, or maybe down. You think you could do it yourself. You know, then 4 people come walking by, and you're like, I just need 2 of you to come help me out. They're like, okay, it'll be me first and then Timmy. I don't care what order you come in, I need 2 of you. Come on, I'm dying over here, you know? So that would be, it's a simple application or instance of it, but that would be a case where I would not care what order the individuals were selected in, just that they were selected. All right, so I have A then B, so I don't need B then A. Well, I might still need the B. So I don't need this outcome. All right. If I have A then C, I don't need C then A. If I have A then D, I don't need D then A, because they're repeats. It's the same group of individuals, just in a different order. All right. In the case of the daily number, the first ball up is 2, and the second, I do care about the order, because if I select the number 1, 2, 3, and I do a straight bet on it, 3, 2, 1 comes up, I lose. All right. There are ways to, hedge your bet. So we'll talk about that as we go. But in the case of like Powerball, it's just the numbers. It doesn't matter what order it comes up in. It's because there's many more numbers that need to be selected. It doesn't matter what order they're selected in, just that you get those numbers. All right. So BC, already have it, or CB is the same as BC. Doesn't add anything to the conversation if I write it again, so we're going to eliminate it. BD, DB, CD, DC. All right, so the unique pairings here are AB, I'll use a comma, AC, AD, BC, BD, and CD. So when we wanted all 4 people in every possible arrangement, we had 24 outcomes. When we only wanted 2 of them, but we cared about what order they came in, we went down to 12 outcomes. Now we're down to a total of 6 outcomes, because now I'm saying I don't care what order they're selected in, I just want the individuals. All right. So these are my 6 unique pairings. But we want to think about a way that we could get there quicker. All right. So again, I did the whole copy paste thing. I erased parts of the tree diagram. I used it repeatedly. If I'm comfortable with the concepts of factorials and permutations and now combinations, I can get to the number without doing all the work. All right. So what we would use is the combination. It's in the same menu. So in the same menu, you'll see the N over K. All right, so same menu. Almost put an E at the end of menu. That wouldn't have been good. We want the N over K. The N represent, it's really just going to boil down to what we said for permutations. N is the number of individuals. available. K is the number of positions in each group. All right. So combinations, we want to be thinking about groups of individuals where we don't care about what order they're selected in. The example that I usually give, just staying away from lotteries for a second, is if I wanted to break you all up into groups, break the students of a class into groups of, let's say, 3, and I say one group is Tommy, Jimmy, and Colin, and the second group is Colin, Jimmy, and Tommy, and the third group would be Colin, Tommy, then Jimmy. Like I wouldn't say all the arrangements because I put the same 3 people in 3 different groups. That doesn't make sense. All right, so this eliminates those repeats. So in this case, what I would do is 4 over 2 in that in those round brackets. So n over k, it brings up a little feel. It kind of looks like a fraction, and you sort of treat it the same way. Put the top number in, the bottom number, but it's not a fraction. It just gives you the total count of individuals in each category, or each group is what I should say. I mean, a category makes sense, but it's not consistent with my example, right? Benefit of something like this is if I had 40 people and I want to put them in groups of 5, it's going to spit out the total number of possible combinations that I could have. Right, which is really, in this context, beneficial to have a tool that'll do it for us, because, yeah, the tree diagram took a few minutes to draw out, and then, from your perspective, if you drew the truncated one and you did that a couple times, it took a few minutes. Here we can still get at the number without having to do the visual part of it. All right. Well, think about a game like 5-card poker, if you're familiar with that. And you might care about the order in which cards come out, but there's 52 cards in a deck, and you want 5 cards. There is a little over 2.5 million possible 5-card hands that exist. All right, so if you're the first person to get, I mean, it doesn't really work that way, because you work around the table, you deal it out, one person gets a card, and you do it until each person has the total number of cards. But like, you just imagine that you just took a well shuffled deck and dealt out 5 cards, and you're looking for the probability, just for fun, the probability of getting a flush, the probability of getting a straight flush, the probability of getting 2 pair, things like that. This will give you the total number of possible hands that you could be dealt, right? And again, you don't care about the order that they come out in this context, because what do? If you get, let's say, 2 2s, an ace, and let's say a jack and a queen, you're probably going to rearrange your hand so that the 2 2s are next to each other. And the others, you don't care about the order, right? So, it's a case where it doesn't matter in what way the cards were dealt to you. It's just that you get what, you're hoping to get. A more realistic application of it is, let's say you're playing. I'll go with blackjack, I guess. I wanted to say Texas Hold'em, but I mean most people at least have some familiarity with the game of 21 blackjack. You want your cards to add up to 21 or be the closest to it without going over. So let's say you already have 2 cards, and one of them's a jack and the other's a 5, so you're up to 15. So and you know how many cards have been dealt, which is actually pretty easy to track. Then you can kind of at least have an intuitive understanding of the probability of getting a card or set of cards that will add up to 6 to get you to the 21. Right? So just having that awareness. I mean, you're not going to sit there. I mean, you're really not going to sit there calculating it. That they will not let that happen, right? But you could have an idea, right? Well, I've already seen 2 6s out. Right? I've seen all the available 2s are out, 3s are out. I don't see how I'm getting a 6, So it informs your decision, right? I mean, you can apply this in a number of different ways, but it has to be cases that are dependent, right? When you're using combinations and permutations, right? Because if you're dealing with you're rolling a die, like you don't remove possible outcomes based off of your previous result. Like if you roll a 6, it doesn't mean you can't roll a 6 again. It's not like you used the 6. Right? So that would be a different story, but yeah, there are a lot of applications of this, and I'll show you. I keep saying I'll show you. I will, I promise. It's just we get through the foundational stuff first. Right? So the example 4 there is 10 students are in a class. Determine the number of 3-person groups that could be generated from the available students. Right? So that would be 10. It's a 3-person group, so that would be this computation. And again, toolbox, and I'll bring it right from the beginning. All right, so first time you're using the toolbox in NumWorks, you select toolbox, you go down to probability, combinatorics, and this is a combination, so that's the first one I want. 10, 3, hit OK. We have 120 possible outcomes. All right, 120 different possible combinations. So you just think back to when you were a student in middle school and maybe early high school, and you got put in a group and that group did not contain any one of your friends. Maybe you're a little chatty in class, and a teacher said, no, I randomly created these groups. Even for 10 students in a class in total, there would be 120 different possible combinations. The likelihood that the teacher randomly put you in a group with two of the people that you hate most in the world, knowing that you're not going to get off track because you're not going to get into side conversations, the chances of that happening are so remote that the teacher must have been lying. Right? Now, common sense tells you that's probably the case anyway, but it's confirmed with the math. Right? Now, jack this up to typical high school class, 25 students these days. Groups of 3 is pretty typical. 2,300 different ways that this teacher could put you into groups. And again, you didn't get, let's say you have 7 or 8 friends in the class, and you're grouped with none of them. The chances of that happening are so remote that it's just not true. There was no randomization involved. And so this is another application of probability, is the proof or disproof. Can't really prove, but we can reasonably disprove when somebody says that something is random. All right? And that's, going back to casino games, if you win too much in the same kind of way over and over again, which usually when people try to cheat at casinos, they have a plan going in. But the plan is not, okay, I'm going to use these 15 different strategies. You have 1 or 2 strategies. You're not supposed to win very often. Just in general, gambling, casinos, the house always wins. So if you're winning consistently, and the probability of you winning is so very remote that it shouldn't be happening, that's when somebody pays you a visit. Right? Because they could just tell by the numbers. So they know something is off. They'll say, stop doing what you're doing. That was your only warning, and that was it. But anyway, more on that later. Number of 7-person groups that can be generated from the available students. So 7-person groups. You're going to get a result of 120. A little eyelash there, sorry. So 7. Also 120. All right, which is kind of strange. You look at it and say, well, I guess it's possible that two different sets of parameters could lead to the same outcome, but why? So I look at this as saying, if you have 10 people and you select a group of 3, you're indirectly also selecting a group of 7. The 7 people that you didn't want to be in the group of 3. All right? So for every group of 3 that you could have, there's a hidden group of 7 that could also have occurred. Like if I give you like 5 cards, let's say a 10, Jack, Queen, King, and Ace, and I tell you to give me a list of every possible group of 3 that you could have out of that. All right? Every possible group of 3. So maybe 10 Jack Queen, 10 Jack King, 10 Jack Ace, and so on. Like every possible group of 3. There's always 2 cards that are left over that haven't been accounted for, but they're still going to amount to the same number of outcomes that you could have for the group of 3. All right? So this gets us to the idea that sometimes it's more beneficial to find the probability of the thing that you're not looking for, subtract it from 1, because 1 is 100% total number of possible outcomes, and that'll give you the probability of the thing that you are looking for. All right? So in the form of combinatorics, find the number of ways to come up with a combination of the things that you don't want, and that will equate to the number of combinations of things that you do want. All right? So this is just really a generalization of what I was saying, so don't really need too much of that. We have some shortcut rules. These are completely optional, but they are pretty nifty if you recognize a shortcut rule. Nifty in the sense that in the real world, if you're going to try to apply mathematical concepts, you're probably not going to have a calculator with you. And I don't mean the one that's built into your phone. Like the NumWorks calculator. I imagine when this course is over, that's the first thing to get deleted. But maybe, just having an awareness of it is like, oh, actually, I do have to do some serious computation. Later on in the course, I'm going to teach you about amortization, mortgages, interest rates, and things like that. And this particular calculator is a pretty good app that'll do that for you. And I can tell you, I mean, it wasn't this calculator, but when I was buying my first house, like how much can I afford to spend each month? Right? What does that equate to in terms of a mortgage? Like if I know I have to take out a loan for, let's say, $500,000, what does that equate to in terms of a monthly payment? Can I afford that? Right? The better way is to figure out how much you have on a monthly basis and use that to dictate the value of the house that you should be purchasing. Right? That's the whole living within your means kind of situation. So I whipped out my old graphing calculator and I sat there, and it broke my wife's heart when she found out that there was no chance we'd be able to sustainably afford the place that she absolutely fell in love with. So we got the second place that she kind of fell in love with. And we're still there, so it's been good, but you make concessions based off of these things. So yeah, are you going to whip out the graphing calculator to compute the tip when you go out to the restaurant? No, you just use a simple one on your phone, right? Or you use the tricks like double the tax, or slide a decimal over one place and go that route. That's all well and good, but when it comes to the heavy duty stuff, you probably need some computing technology, and NumWorks might be the one that you use. Right? So again, these shortcut rules, they're great. Like knowing that, notation. I used to use the TI calculator, now I use NumWorks, and they represent a combination a different way. So this one here is the same as saying n over 0 is equal to 1. So if I do a combination, let's say I have 10 students, but I want none of them in a group. I get a result of 1. All right? And you think about it, how can you have any possible outcomes if you were to say there are 10 people and I want them in groups of none? I could say, well, there's one way. That's the one group of none. But I could look at it this way. If I have 10 students and I want a group of none, that's going to be the same as 10 students in groups of 10. All right? Because again, this is what we want. This is what we don't want. But for every combination of something we want, there is a combination involving something we don't want. All right. So that goes back to what I was saying. If you have groups of 3, well, I selected 3 people. That means I consciously chose not to select the other 7 people. So a group of 3 corresponds to a group of 7, the wants, the don't wants. All right. So I have a group of 10. Well, that's everyone. There's only one way I can get a group of 10 from 10 people. All right. For that one group, there is naturally the corresponding group that contains none. So since these two things are the same, that means that N0 and NN are both equal to 1. They're equal to the same thing. Those are probably the most powerful ones. All right. 0 factorial is equal to 1. That one doesn't really work for a lot of people, but that's a true relationship. You could test it in the calculator. All right. So it's along the same ideas of why the combination of 0 individuals per group is equal to 1. All right. There's a proof for it. I'll jot it down in the notes, but it's not something that you would need to be able to do, so I don't want to waste any time with that. So on the next page, I get a bunch of examples, and then you see at the bottom I have a quizzes. All right, so a quizzes is not a quiz. All right, it's not a typo for a quiz. Some of you may have heard of this before. It's an online sort of quiz, but it's more like a game. You get unlimited attempts, so that's not something to be afraid of. All right, so you'll see that for some of the pages at the bottom, it'll say, like what the activity is. You don't have to start worrying about it until I tell you, but I did post this one because I think we're going to get there. Yeah. Anyway, let's do a few examples. So, and just to, and actually I'm going to selected 9 players for a baseball team. How many possible batting orders are there? Like some of the examples I use, you see a lot of sports in there, a lot of card playing and stuff like that. I know not everybody's familiar with it, but it's, I try to do something that I think most people know about. So you have 9 players who bat in a game of baseball, if you don't know. Right? And the manager decides what order that they're going to bat in based off their strengths, and if they're a contact hitter, they hit the ball a lot, but they don't hit it far, or maybe they hit home runs a lot, but they strike out a lot too. A lot of different possibilities. So the batting order is predetermined. We're just trying to figure out, assuming all the players are of equal ability, what would be the number of possible orders that you could have. So this goes back to the factorial question, right? So if I were to make a tree diagram out of this, it'd be monstrous. I'm just going to say 9 individuals, factorial, right? And then compute that. And the reason why it's a factorial is because every one of the 9 players are going to be accounted for here, right? And I do care about the order. So all players are accounted for. None of them are getting eliminated. And order is important. Now, that last little bit there, I know if you're not really into baseball, you might not recognize that, the order matters. If it were on a quiz or something like that, a test down the line, I'd choose an example that I know everybody could relate to, or I'd really explain the living daylights out of it, like the structure of the game. It's just in baseball, and really a lot of sports, like hockey too, depending on where you are in the rotation, that dictates how much playing time you get. All right. So if you're the first person, if you're a starter, you're going to get more playing time than somebody who's in a backup role. All right. And so in theory, the starter should be a better player than the person who's in the backup, although, that doesn't always end up being the case. All right. So there are 362,880 possible lineups. All right. So somehow the manager has to sift through all of that and come up with the winning permutation. If the pitcher must bat last, how many possible batting orders are there? Well, that's telling me that I'm starting with 9 and I only really care about placing 8 of them. Right? So, and you could kind of diagram it out if you want to. This is something that I do sometimes. You have 1, 2, 3, 4, 5, 6, 7, 8, and then you have the pitcher. All right. So we're saying that
This one we just do the same thing as we did up there, but maybe 8 factorial.
exactly. Yeah. So if you diagram it out like a mini diagram, you'd start off with 8 individuals, and then you'd go down the line until you get to 1, and that would give you the 8 factorial. All right. So the way I wrote it out here, it's not something that you would need to do. It's just a little extra visual for you. All right. So 8 factorial, the pitcher is irrelevant. That person has already been placed into a position, so we don't need to consider that. All right. So 8 factorial gives us 40,320. So it's an improvement. Now, consider going a little bit further with this, and I'm not going to ask you to, but let's say you want Pete Alonso batting third, you want Francisco Lindor batting, let's say, second, Starling Marte is going to be your leadoff, but then after that, you're like, okay, I don't know, I'm going to put McNeil here, who am I going to put in? So you can eliminate lots of these possible variations by slotting in players to positions that you're comfortable with, and then everyone else you just permute. Like, okay, throw the names in a hat, and we'll figure it out from there. All right, so little Mets reference there for you. Compute the probability. So now it's probability, not number of ways, but probability. And you could also look at this as, in number 1, A and B, a probability instance where you'd say, all right, well, the manager just said that I randomly put the kids, I created a batting order and it was completely at random. But, like let's say it's Little League. But somehow the manager's son is always the leadoff hitter. You're like, okay, so what are the chances that this person randomly came up with a batting order and every single time his kid was in the leadoff position? He's lying. It's not random. All right. Professional level, they have to be a little bit more anchored to the numbers because the manager's job's on the line. So compute the probability of randomly drawing 5 cards from a deck and getting exactly 1 ace. All right, so we're randomly drawing 5 cards from a deck, and we're going to get exactly 1 ace. So we can look at the different ways in which you can get an ace. All right, it may be the first card that's an ace. It may be only the second, the third, the fourth, or the fifth. All right. So what I like to do until we get to binomial probability, and I'll keep it simple, but I'm gonna diagram this out. So and say I'm gonna get an ace as my first card, and then not an ace, not an ace, not an ace, not an ace. All right, that's one possible way you could get 5 cards where there's exactly 1 ace. All right. Maybe it's the second card that's the ace, and everything else is not an ace. Maybe it's the third card. Fourth card and fifth card. All right, so just thinking about where I should put it. So not ace, not ace, not ace, not ace. Oh, sorry, ace, not ace. Just trying to be a little systematic about this. So then not ace, not ace, not ace, not ace, finally an ace. Size it to fit. All right, so in each instance here, we're looking at getting 4 cards that are not aces and 1 card that is an ace. All right, so for the probability, I would say, and I'll just look at the first instance. The first card is an ace. You have a 4 in 52 chance of getting that card. The second, third, fourth, and fifth cards are not aces. So you got to think about all the cards that are not aces in general, what you have and what you need. All right. There's 48 cards that are not aces. If 4 of them are aces, the other 48 must not be. So the first card could be 48 out of 51, all right, because we removed 1 card from the set. Then we could have 47 out of 50, 46 out of 49, because we're removing 1 card from the set. Every time we withdraw a card from the set, it's in our possession. It's no longer in the deck. All right, then 45 out of 48. All right, so you could do it systematically like that. But then, you know, it's always going to beg the question: what if it's 10 cards drawn from a deck? Now it just became much lengthier. So we want to trim this down a little bit. So this is where we have the expansion, and we want to determine the simpler way of writing it, right? And then use that to help us figure out other problems. So we're starting on the top here, starting off with a 48. And get a thinner marker here. 48 down to 47, 46, 45. All right. If it went all the way down to 1, that would be a factorial. It doesn't. So we used a limitation of a factorial, a truncated factorial. So what we do here is we say that we're going to permute. Remember, the definition or the parameters for permuting is how many you have available, how many individuals are available. We have 48 cards available. And how many slots, how many positions are available. Well, I highlighted 4 things, so there's 4 positions available. So that accounts for most of the top. I still have a 4 there, so I'm going to just multiply by 4. Then on the bottom, I'm starting off with a 52, going to 51, 50, 49, 48. If I could go all the way down to 1, it would be a factorial. I'm not. I'm cutting it short. I'm limiting the factorial. So it must be a permutation starting with 52. And there are 5 positions available, right? 5 cards that are being selected. Now, we would just have to do that 4 more times because, remember, we only accounted for this first set here. Right? So instead of doing, because, you know, the second set, third, fourth, and fifth, they're all made up of these same ingredients. So it's not going to be any different. So I have 1, 2, 3, 4, 5 possible sets. So I would multiply this by 5. All right. So we'll have to figure out how we get that 5 there in a minute. But before we do that, we'll just do the computation. So I'm taking 5, multiplying it by I'll make the fraction bar. Oh, no, I don't want to do that. I guess I'll put the 4 nope. I'll multiply by 5 after the fact. 4 times toolbox permute 48 4. We're going to divide that by permute 52 4, and then multiply all that by 5. Let's do it that way. Put it in after the fact. All right. And then when we hit OK, we get our probability. Yeah. Something went wrong here.
It's supposed to be 52.5, right?
5, yep. I appreciate that. Yeah, there we go. Yeah, so one quick and easy way to determine if you just screwed something up is if you get a number that's bigger than 1 or less than 0, probabilities can only be between 0 and 1. So when I saw that 14.374, I knew something went wrong. Right, so that's step 1. Step 2 is figuring out how to fix it. So about 0.299, and you know, like the decimal form is nice. Fractional form is good too. Either way, when you're dealing with call it real life cases, you probably want to at least be aware of what the decimal equivalent is, because that's how people think typically. You know, so I'm saying that there's a 30% chance that if I'm dealt a hand of 5 cards, I'll get exactly 1 ace. All right. Now, why would that be important? I have no idea. All right. It's really more like, you know, you're talking about a deck of cards. You're playing poker, blackjack, or whatever. You're looking for a particular outcome. But in poker, you usually want to have more than one of the same outcome. So I wouldn't want just 1 ace. Maybe I want 3 aces. Yeah. So that leads us to the second example. Well, the second probability example, third one overall. Compute the probability of randomly drawing 5 cards from a deck and getting exactly 2 aces. All right, so we could do what we did above here and list all these possibilities out. But I mentioned before that I wanted to figure out where that 5 came from. I've already used these colors. Let me get green involved. All right, how would I know that this is a 5 without having to make this entire list? Well, we had 5 cards available, and we wanted to determine the number of instances in which you would get an ace. All right. So what ends up being the case is that this is a combination 5 and 1. All right. So 5 cards broken up into really groups of 1. That gives you a result of 5. Because there's only the 1 ace that I want, right? So 5 of the cards, that gives me the top number. That's the number of possibilities in groups of 1, specifically focusing on the case of getting an ace, right? So when we do this for this part of it, and we say that we want to get exactly 2 aces, we can do what we did before and say, all right, you know, ace, ace. I'll do a couple of instances. Ace, ace, not ace, not ace, not ace. But then I'd have to account for the number of ways that I can get 2 aces out of the 5 cards. So maybe it's ace, ace in the second and third position, surrounded by a bunch of not aces. Maybe it's the first and third card that are aces and everything else is not ace. It adds up pretty quickly. All right. But if I say that I want 5 C, old habits die hard, combination 5-2, 5 cards, 2 of which are aces, this will give me the number of possible ways that could be. So this will give me a total of 10. So it would be 1, 2, 3. If I listed them all out, ... I'd end up with a total of 10. All right, so it's a time saver. But then I have to account for the permutations. All right, so I'm going to have 2 aces in a set. So there's a 4 out of 52 for the first ace, a 3 out of 51 for the second ace. All right, I'm going to put this down here for a second. So we know that this is going to be 10, but let's just focus on the first case here. So 4 out of 52 for the first ace, 3 out of 51 for the second ace. Then after that, it could be anything else that's not an ace. And again, we start off with 48 non-aces. But there's only 50 cards left over. Then 47 non-aces, 49 cards left over. And then 46 non-aces, 48 cards left over. Yeah.
Why is it 4 over 52 and not 3?
This one?
Yeah.
4 over 52 and not what?
3 over.
Because if we're starting off with a fresh deck, the probability of getting an ace, there's 4 aces, there's 52 cards.
Oh.
The second one would be 3 because then we will have removed one from the deck. All right, so here we have 3 components, but it's all going to clean up to a nice shortcut in a little bit. All right, so the first component here is that we have a 4 times a 3. Now you could just look at that as a 4 times 3, but you could also look at it as a permutation. All right, so I'm going to bring this back up. That 4, 3 is permuting, starting with a 4 and having 2 positions available. All right. Then we're looking at the 48, 47, 46. That's permute, starting with 48 and three positions being available. The bottom is going to be what it was before, starting off with 52, and you have 5 positions available. All right, and then we would run this through the calculator. I know it's kind of a mess, but we'll run it through and we'll get the results. And again, like we're doing this for a purpose, to kind of learn the notation and how to function using permutations and combinations. But if you were doing this out by hand, you would probably just multiply across the top, multiply across the bottom, and be done with it. All right. I guess that's where a little bit of trust comes into play. So I put 5, 2. Then I'm doing permute. 4, 2. Permute. 48, 3. Divide. Permute. It's not pretty to have the 5 combination 2 up top, but it's still correct. Oops, I already have the comment there. All right, so this gets a little beefier, but it gives you a valid probability of 0.0399. All right. Again, it's not pretty, but it gets the job done. And so, we could kind of generalize a little bit, but we'd be generalizing to just this type of question. Like aces taken from a deck, or maybe only kings taken from a deck, or jacks, or whatever. Like it really doesn't make a difference. But in each case, you have something relevant to the problem. You have the number of aces that you have and the number of aces that you want. All right, the number of other cards that you have and the number of other cards that you want. The number of ways that you can get an ace as one of the 5 selection, or 2 aces, sorry, as one of the selections from the 5 possible outcomes, and then the number of ways you could select cards from a deck in general. All right. So, I mean, it's one thing to have a formula that you could use to solve a problem. It's another thing to say, I'm going to memorize this particular formula for this particular type of problem that's probably never going to happen in real life. Yeah, I'll pass on that. Right. So what we do is we use this for the more complicated situations so that we don't have to, and by complicated, I mean larger numbers, larger possible outcomes. So if I tell you that you have 300 candidates for a job, or, I'm sorry, 300 candidates for 10 jobs, and they're all equal ability. What's my probability of being one of the ones that are selected? You know, that's along the lines of what this is talking about. Let's see. 4 and 5. Oh, well, 4 is definitely just a rehash of this, so I'm going to skip that for now. I'll save it for next time. It's always good to have a wraparound problem. But yeah, I guess we could do the birthday ones now. All right, so let's start off with number 5. And this is where you can see that you can generalize pretty nicely. Suppose 3 people are in a room. What's the probability that there's at least one shared birthday among these 3 people? All right, so birthday, not birth date. Right, it's very, very remote that you'd have the same actual birth date, but you could have the same birthday. So if there's only 3 people, you know, like your senses would tell you, okay, it's not likely. You know, so how do we figure that out? Well, the first person could be born on any day out of the year. Any 365 of those 365 days. All right. The second person could be born on any other day except for the first person. So the second person could be born on 364 of the 365 days. We don't bother with leap years. Right? And the third person can be born on any of the remaining 363 days out of the 365 days. So on the top, and this is the value of the permutation, because you can see the next problem is going to have 5 people, and the problem after that is going to have 20 people. Now, you intuitively would know that the probability is going to improve of having a matching birthday the more people that you have in the room, right? But in what way, and how could we figure it out? So if we look at the top as being a permute, we have 365 individuals, those individuals being days, and there's 3 positions available. We would say permute 365, 3. But on the bottom, there is no decrease, right? Because I'm not removing days from the year. Those days are going to stay put. I'm removing possible days that a person could be born on. Right? But it is still out of the number of possible days available. Right? So, I mean, I give you the quick for instance. What's the probability that you're going to guess my birthday? Well, there's only one of them that's relevant, and there's 365 that are available. So you have a 1 in 365 probability of guessing my birthday. Now, if I tell you it's in the late summer, you're like, okay, so that's going to get me August, maybe September. Now you've just trimmed it down a little bit, so that adds a conditional, but it's still something that you'd have to compute by the numbers. But on the bottom, we're just doing a 365 to the 3rd power. All right, multiply a number by itself, you can raise it to a power. And I'll crunch these numbers in a minute, but I can tell you that since that first value here, this represents the number of days in a year, and so does the one on the bottom, obviously. This 3 represents the number of people corresponding with the power on the bottom. Now we have a rule. All right, so in this case, I would say permute 365. Now we have 5 people. Number of days in the year isn't going to change, but the number of people in the room will change. So why would it be any different if I have 20 people in a room? It's going to be the same structure every time. So now it's just a matter of running it through the computer. So permute 365, start off with the 3, divide it by 365 raised to the third. And again, we could have done this the way we did the ACE question, where we figure out the probability of each one. But we did it that one time here to come up with a rule that'll help us figure it out for all the complicated cases after that. All right. So about a 99% chance that they're going to have no birthdays in common. And I'll get to the part where we talk about at least one, because that's the second step to each one of these. It's a quick one, though, so that's why I kind of glossed over it. / I forgot about it. Oh, I don't like this. Okay, we'll go back to the original. Oh, clear that. Come on, clear it out. Dang it. Let's do this real quick. I copied the wrong one. So this is going to be to the 5th power. So now we're up to about 0.973. And then we're doing it with 20 people in the room. So about 0.589. All right. So these are the probabilities that all the birthdays would be different. All right. So probability not equal. All right. So probability that are all different. I want the probability that there's going to be at least one birthday in common. All right. So the way we would handle that, so probability at least one shared is going to be 1 minus the probability that they're all different. That's going to be 0.008. Oh, sorry. So, in terms of common sense, you know that the probability is going to be small, that they'll have a common birthday. Probability is going to be pretty large that their birthdays are going to be different. But as we increase the number of people in our sample, the probability changes. So 0.973 subtracted from 1 would be 0.027. And then subtracting 0.589, that's going to give me a 0.41, 421, no, 411. Yeah. All right, so the probability that there would be at least one common birthday just went from virtually impossible to, it's close to a 50-50 chance now. All right. So if you have 100 people in a room, 200, you're going to improve your probability. You'll make it a guarantee if you have more than 365 people in a room. That's like a good question. What is it? The fortune tellers, the people who do the shows, and they bring someone up on the stage and tell them, oh, you're likely to marry this person by this age, and like those kind of people. Like if they know that there's more than 365 people in a room, they say, I predict that there's a person in here with a birthday of September whatever, or they could say, I predict that there's two people in the room that have the same birthday, and so it becomes a virtual guarantee the higher you get, but then it becomes guaranteed once you get over 365, assuming you don't count for the leap years. So that